Hello and welcome to the third and final video for C1 and C2 for GCSE Combined Science. Now in this video we're going to have a look at the periodic table, including the development of it, the noble gases, the alkali metals and the halogens. Now to start off, obviously I would like your teacher to please pause the video so you can complete these three questions. The answers are now on screen. Well done for getting all three of those correct. If you're ready, we shall begin. And we're going to start off looking at the periodic table. Now there is a session recorded for this on the CHSG YouTube channel as well, if you need more information and want to go over it a bit more. But we've got the periodic table. We've got our modern periodic table, how we use it. And we can split it up into a variety of ways. We've got different groups going down. So the groups go down. And all of the elements in certain groups have similar properties. We can also draw a stepped line across here. And we've got metals, and we've got non-metals. Loads of different ways we can do it. But the important thing is, it will organise the elements, and it organises them in a particular way. We go in order of increasing atomic number, so the number of protons in each atom. We start at 1, and you can see we go all the way up to 118 at the end. It also puts them into groups of similar elements, so elements that behave in similar ways, and we'll have a little look at that in a second. Now the modern periodic table that we have is based on the one made by Dmitry Mendeleev. Now you might remember that there's been numerous ideas about how we could organise them. We had the triads, we had and the octaves, Newland's octaves, loads of different ways to do it, and none of them were quite right. And this Russian guy, Dmitry Mendeleev, came along and said, aha, I've worked out how to do it. And he put them in order of increasing mass. And when he did that, he left some gaps as well, because he worked out that there were some elements that weren't quite right, or that didn't fit yet, hadn't been discovered. So he was like, oh, I'll leave the gaps. And he could then predict what properties those elements would have based on where they'd appeared in the table. Now you might be thinking, well, why did he do it by mass and not by atomic number? This was in the 1860s. We'd not discovered the proton. We'd not discovered the electron. Or we'd definitely not discovered the neutron. All we knew was what Dalton had for his theory of the atoms, was that they were tiny, hard spheres. That's all we knew. And we knew how much they weighed compared to other atoms. And that's why we did it that way. Now, the problem Mendeleev had was that some of the elements he organised were out of order. And they are now for their mass number. And he had to put them in a certain way so they were in the correct group. So for example, iodine and tellurium, their mass numbers are the wrong way round. Their proton numbers are correct, but the mass numbers are the wrong way round. It's all because we ended up discovering, about 50, 60 years later, isotopes and how they have different masses for the same element, and it caused a few problems. The masses we have on the table are the most common isotope, not the lightest one, as it were. But as we direct that, it made a bit more sense and we understood it, so he was right to put things in certain places, even if he didn't understand why. So I would now need you to please your teacher to please pause the video so you can answer these questions. You should now be able to mark your answers. And we're now going to have a look at some different groups of elements. The first one we're going to have a look at are the noble gases. That is group 0. So the group 0 elements are known as the noble gases. Now they all have a full outer shell of electrons. You remember that would be 8 electrons, apart from the helium, which only has 2. Why does it only have 2? Because that first outer shell is just 2 electrons. Our noble gases are very unreactive. That is because they don't need to lose or gain. So they won't. Let's write that properly. So they won't lose or gain electrons. And they don't need to share electrons. So they are very unreactive. And instead of unreactive, we can use a better word. We can say they are inert, because they have a full outer shell of electrons, so they won't lose or gain, and don't need to share any electrons. Now they have very, very low melting and boiling points. They're all gases at room temperature. As we go down the group, the boiling point will increase. A problem we have with noble gases is that they are colourless, so we can't see them, and they are inert. They do not react with anything, so they are very difficult to detect. They are also poor conductors of heat and electricity. There's no delocalized electrons or free or charged particles to move to carry a current. And because they are a gas at room temperature and even lower, there is a lot of space between the particles, so heat cannot conduct through them easily. Please pause the video now to answer these questions. You should now be ready to mark your answers. We're now going to have a look at another group of elements. So our group 1 elements, those first ones we find on the periodic table, are known as the alkali metals. You've probably met them before. They do react quite well with water. Now they all have 1 electron in their outer shell. We know that because they're in group 1, so they have 1 electron in their outer shell. As we go down the group, we have a trend happening here. The reactivity increases as we go down the group. And they all form positively charged ions. So we have our group 1 elements here. I'm going to have a look at why that reactivity increases. So we've got lithium here. I've got my 3 electrons. We'll have a look at, we'll go for potassium, because that's going to be more reactive. And I've got quite a few more shells before I get to that electron. Now for these atoms to react, they need to lose the electron. So they will lose the electron, so that outer electron, to react. As we have a look, lithium, we have an outer electron is very, very close to the nucleus. I have a positive nucleus and a negative electron, so we have a strong attraction. I also don't have very many electrons in the way that are stopping that force, that attractive force. Time we look at potassium, I am a lot further away. I have a larger distance, so my force of attraction is weaker. So my electrostatic force is weaker. This means this electron is a lot easier to take away from potassium than it is from lithium. As we get down to francium, that outer electron is even further away, so it becomes even more reactive because it's very, very easy to lose that outer electron. So first up, reacting with water. It's a very vigorous reaction. You might have seen it either in previous years or heard about it when we had the fire alarm going off just over a year ago, which is down to me setting it off in one of the C rooms. So we'll have a look. I have here a trough of water, and I'm going to get my alkali metal and I'm going to pop it in. Now, if we start off with lithium, we get some fizzing. That fizzing is our hydrogen gas being given off. And we've turned our water into lithium hydroxide. We have a think about the other ones as we go further down. We get sodium and potassium, so we'll have a look at potassium and what's happening there. So we'll get some potassium. We'll drop that in. Again, it will give off the hydrogen. As it reacts, it will turn this into potassium hydroxide. And you might remember that we end up getting a purple flame. You might think, why do we get a purple flame? The reason is the reaction releases so much energy, it causes the hydrogen to ignite. The purple colour comes from the potassium ions, which give off a purple colour when they are heated or combusted. Now, we have some word equations to learn. We have a generic word equation. We get our metal plus water makes our hydrogen plus metal hydroxide, or alkali metal hydroxide. All we have to do is change our words here. So we have lithium plus water will make hydrogen plus lithium hydroxide. Sodium plus water will make hydrogen plus sodium hydroxide. Potassium plus water will make hydrogen plus potassium hydroxide. Exactly the same. We also have a balanced symbol equation. Now, looking at this, you might go, oh, hang on, Mr. Lewis, that's not balanced. You're right, it's not balanced. We do need to balance it. If you're not sure about balancing, do go and look at the balancing equations video that we've done in using the boxes. But to balance this, we're going to put a 2 in front of here to make sure we've got the right number of hydrogens on each side. We'll have a 2 in front of there and a 2 in front of there as well. They are all now balanced. We've got 4 hydrogens on each side, and we've got 2 lithiums and 2 oxygens on each side. So, reacting alkali metals with oxygen. This is an oxidation reaction. If we react anything with oxygen, we can say it's an oxidation reaction. Now, our alkali metals, as we find them, are very, very shiny. If we add them to some oxygen that we have just floating around in the air, our metal, instead of being shiny, becomes very, very dull. We can say it has been tarnished. This reaction happens very, very quickly. It's why we keep or one of the reasons why we keep our alkali metals in oil, to stop them reacting with oxygen and also any water very, very quickly. Our general word equation is our metal plus oxygen will make a metal oxide. I've done one here for lithium. So lithium plus oxygen will make lithium oxide. We have our symbol equation as well. And what we can do, we're going to even add our state symbols to it as well. We also need to make sure that it is balanced. I've got 2 oxygens on this side, so I need to make sure I have 2 on this side as well. So I'll put a big 2 there. I've now got 4 lithiums on my right, so I need to put 4 there as well. That is my balanced symbol equation. Again, same for doing it for any of the other ones as well. So for potassium, we would have 4 potassiums plus oxygen would make 2 potassium oxide. Next up, we're going to have a look at reacting our alkali metals with chlorine. When we react them with chlorine, we make a metal chloride. Now, to do this, we need to heat up our alkali metals. So we don't often do it in school because it's a little bit dangerous. But if we heat up our alkali metals and add it to chlorine gas, we will react them together to make a metal chloride. So we have a metal plus chlorine will make a metal chloride. Again, I'm using lithium. Got lithium plus chlorine will make lithium chloride. Again, we've got our symbol equation. So let's just add our state symbols. And again, let's make sure we are balanced. We've got 2 chlorines on both sides now and 2 lithiums on both sides. Again, same principle for any other alkali metal and writing our equations. We just need to change whatever this is and whatever that is. Now, please pause the video to answer these 4 questions. The answers will now be on screen. Please pause the video to answer the next 4 questions. The answers are now appearing on screen. We're now going to have a look at the halogens, which are the group 7 elements. Group 7, known as the halogens. Now, all the halogens have 7 electrons in their outer shell. And they have similar properties to each other as well. Going down the group, this time, however, our reactivity decreases. So not like the alkali metals where it increases, it now decreases going down the group. The boiling point increases as we go down the group. So fluorine, as we find it in room temperature, is a gas. Iodine has become a liquid. And astatine is a solid. Chlorine and bromine are that gas as well. Now they are diatomic molecules. This means they go in pairs. The reason they go in pairs is because they want to share electrons. They will share 1 electron from their outer shell each to make sure that they are then stable. And they will form negatively charged ions with a -1 charge. Our next bit, an important thing to use for displacements, a more reactive halogen will displace a less reactive halogen. So a halogen at the top, fluorine, is more reactive than chlorine. Chlorine is more reactive than bromine, which is more reactive than iodine, which is more reactive than astatine. So that displacement reaction part, let's have a little look at it. We've got chlorine plus sodium bromide will make bromine plus sodium chloride. It's going to displace the less reactive halogen from the aqueous solution of its salt. Now that part is important. We've got sodium bromide, which is our salt here. We've got sodium and bromine mixed together to make sodium bromide. And I've made it into a salt. So I have dissolved it. Let's dissolve it in water. Now this makes a colourless solution. Now if I take chlorine and add it to its aqueous chlorine, which makes a green solution, if I mix them together, I will get a displacement reaction happening. Because chlorine is more reactive than bromine, it will displace it, it will knock it out of the way, and we will get bromine. That should be an aqueous bromine solution, plus sodium chloride. My sodium chloride solution will be colourless still. Halide solutions are always colourless. My bromine solution, though, will be sort of a yellowy brown colour. We will get a colour change. So in these displacement reactions, we see colour changes happening. Now, please pause the video to answer these questions. The answers are on screen now. Thank you very much for watching. I hope it has been useful and informative for you. Take care, stay safe, and have a great rest of the day. Bye-bye.